Great. Well, thank you so much for having us. It's great to be here. Really enjoying the summit. My name is Daniel Jeavons. I'm the General Manager for Advanced Analytics at Shell. What we're going to do is a bit of a double act here. What I thought we'd try and do is frame up what the problem was we were trying to solve, talk a bit about the business rationale for what we were trying to do. Then we're going to go into a little bit about the algorithm that we put together to solve this particular problem. Wayne's going to walk through some of the technicalities. We're then going to talk a little bit about how we tried to scale that up in Spark, and then we'll talk a little bit more about some of the challenges we had around deploying this as a global solution in production. So let me start first with our business and the challenge that we faced. Within Shell, we have a pretty large global company, obviously. I think everybody knows that. We have a huge number of assets globally, and most of those assets carry some amount of spare part inventory. Now, what do we mean by spare part inventory? This is safety stock, pieces of equipment, if you will, that we store in warehouses so that if something goes wrong on one of these assets, we're able to provide a spare part quickly to get the asset up and running again. Now, the reason we do that is that we operate pretty distributed and pretty complex supply chains where it's not always easy to get a spare part out to the location quickly. And what's more, some of these spare parts are highly specialized pieces of equipment, and therefore they're actually quite hard to get and have very long lead times. And so we have had an inventory optimization or inventory analysis discipline within Shell for some time. But actually, the way that this was being done was pretty inconsistent across the globe. So a lot of inventory levels were set on the basis of recommendations or based on products that vendors provided. We also had a bit of risk aversion from the business in terms of trying to make sure that they always had the right level of stock and therefore stockpiling some of these things, particularly in high oil price environments where the cost of downtime was extremely high. And also we've had the inverse of that where as the oil price dipped, there was actually a need to try and free up working capital. Reducing spare part inventory is one of those ways, but are we reducing the right spare parts? And that was always the question. So the ask came sometime about 18 months ago to say, can we do something about this? Can we use advanced analytics to develop a new tool that allows us to optimize our spare part inventory? And so what we did was we put together an agile working team, and what we were tasked with doing was developing a prototype tool that would work specifically for the Gulf of Mexico in the first instance, for two specific assets called Ursa and Brutus, and develop an algorithm that would provide optimum levels of spare parts for those two assets based on their current operations. And we wanted to do that in a web tool that would allow an inventory analyst to interact with recommendations that came from the algorithms that we were going to build, but also put those algorithms in context and allowed the inventory analyst to look at not just the recommendations, but also the why. So the consumption history of that spare part, the system lead time, also the equipment that it related to, where this was going to be used on the assets. And also, importantly, we wanted them to be able to see the criticality of that equipment. So we started to look from the perspective of the equipment and work backwards to the spare part. So what we did is we developed a tool, which initially was a prototype, and we made that available in a user-friendly format based on a web portal which we built in HTML5. And we developed an algorithm which generated optimum stock levels, and we made that available together with the additional information that I talked about in a portal in a way that they could consume as part of their day-to-day work process. And I'll come back to this at the end because actually that's quite important. For us, we're all about developing digital products that can be used within our processes because that's actually where we get the benefits from deploying the data science. So I'm going to talk briefly about the algorithm that we developed and explain a little bit of the core principles that we pulled together. The issue that we have with spare part inventory is that the distributions that you're dealing with here are not typical. We may only have 3 or 4 observations in terms of the consumption history of a particular spare part over the past 5 years, because these things are only used when something goes wrong or when a maintenance job is executed, and hence it's not a typical inventory optimization problem. So the way we approached this is we approached it in really 3 ways. We looked at the material criticality, and we developed a heuristic model which calculated the criticality of any given material on the basis of a number of feed-ins and different data sources that we had within Shell. We then also looked at the lead time history. We developed a Markov chain-based algorithm to simulate the lead times and to identify the right lead time to use as a feed-in to the model. And we also looked at the demand history, and we used a bootstrapping approach to simulate 10,000 times per spare part inventory item the consumption. And we brought all of that together to calculate, on the basis of the criticality, which we translated into a service level, how many items we would need to have in stock at any one time, and importantly, to calculate the reorder points for the inventory levels. Now, I just talked about something. I didn't actually do the work, he did. So I thought I would get Wayne to come and talk a bit more about how he went about this.
Thanks, Dan. Let me see if I can do a proper job of explaining how it's done. So what we have here is a slightly idealized depiction of restocking dynamics, effectively. And what we have is the inventory levels on the y-axis for a particular material, and you can see over time they're diminished until they cross the threshold, which we refer to as the reorder point. This kicks off reorder, and in, say, 30 days' time, stock levels go up to their maximum level, and the process is repeated again. The time it takes between when you order the part and it arrives back is referred to as the lead time, right? And the key thing we're trying to do here is estimate what is the most appropriate reorder point, right? How many do we need in stock to last us, say, 30 days, okay? And what we want to do there is also estimate the different service levels as well. If it's really critical part, then you want to make sure that it's available 95 or 99% of the time. Less critical, you can live with 80%. Now, this is commonly referred to safety stock analysis, and if you look in the literature, 95% of it, appeals to parametric assumptions, leads you to normality, right? But as Dan's already said, what we have is a different ball game here. Instead of having a small number of materials which are frequently issued, what we have is a large catalogue of sporadically issued goods, materials, right? And therefore we go to a non-parametric approach, so we use the Bootstrap simulation approach. So if it takes 30 days, for example, to reorder, the lead time's 30 days, we sample 30 days from the historic data and repeat that 10,000 times, effectively. Yeah? And we get a distribution from that, and we can pick off the tails. What's the 90% distribution? What's the 95% service level, effectively? An extra level on that as well is that 30 days, the lead time of 30 days is the average. Okay, so sometimes it could be 25, sometimes it could be 35. So we had a two-stage simulation approach where we first simulate what the lead time is, and then we do a bootstrap bootstrap simulation based on that, okay? And of course, what we're going to talk about next is how we scaled up and rolled that out. But the real value in this, I guess, is informed decision-making from this analysis, in that you may need 10 items to be in stock to reach 90% service level, okay? But these things typically have a long tail. You may need, 30 items to reach a 95% service level. So you might need 20 extra items in stock just to meet that extra 5% availability. If it's a non-critical part, then you can live with it. And that is the crux of where the informed decision-making comes from. Okay, back to you, Dan.
Brilliant. Thanks, Wayne. Much better job. So I think the most important thing to recognize here is the business impact of this. So I'm all about using data science to drive business benefits, and this one is a great example of that. So the analysis that Wayne did, what we demonstrated was we could optimize and actually in many cases reduce the levels of spare part inventory that we had by around 14% on average. It's very much an average. It varied from asset to asset. But the calculations were around 14%. And that translated into millions of dollars of potential benefit. Shell has over $1 billion of spare part inventory at any point in time. And if you can take the sort of optimization that we talked about here, the business benefits are pretty spectacular. And we saw straight away as we rolled this out, because we combined the data science Wayne talked about with some of the clear explanations of what we were doing and why this was right, as well as providing them with the decision support information in a single web portal, we were able to deliver millions of dollars of business benefit in a very short period of time. In fact, this proof of concept paid for itself in about 4 weeks, one of the best ever payback times that I've seen. And obviously, we'd only looked purely at the inventory reduction. We didn't look at the impact of actually having the right stock available, which is equally important because that has a far bigger business impact because of the avoidance of downtime. Now, because we did that, the Gulf of Mexico got very excited and we generated a problem for ourselves because, of course, in our proof of concept mode, what we'd done is we'd effectively done it on a very simple laptop. We'd loaded it onto a server. We'd made it available in an HTML5 web portal. It was fine. It worked great in proof of concept mode. It was all a batch. It was very simple. But if we wanted to scale this up, we needed to make it repeatable. And also, Shell has literally millions of spare part inventory stored in different warehouses across the globe. And very quickly, they wanted to turn this into a global tool. And so what we had to do was think of an approach which allowed us to take the work that Wayne had done and scale it up. And I'm just going to summarize the architecture we pulled together. And then what Wayne's going to do is go into a little bit more detail of how we went about doing that using Spark and using Databricks. So what we decided to do was all of our inventory data is stored in our ERP systems. So we leveraged the existing infrastructure that we had, which was our SAP backend and a tool called SAP HANA, which is an in-memory database, to extract all of the base data that we needed. We then used Alteryx to transfer that data into a Databricks environment, well, initially into an S3 storage environment, and then used a Databricks calculation engine before writing the data back into HANA, which we could then run the HTML5 web portal on top of, which gave a very, very performant user interface, as well as some very dynamic in-memory queries. What's important to note also is we had a pretty spectacular scale-up and speed-up capability in Databricks that allowed us to parallelize the R code and really optimize how that was executed at scale, which allowed us to take very, very long-running jobs and make them far more supportable, far more usable. And Wayne's going to talk about exactly how we did that.
Okay, so what we actually have here, if you look across all the materials across the shell, is an embarrassingly parallel problem. Okay, so each material historical data set can be processed independently. Okay, and lesson number 1 here that applies to all architectures we tested is the benefits of chunking effectively. So if you see this depiction here, what we have is the total number of jobs on the left-hand side there, and then we break it down into smaller subsets, right? And then instead of parallelizing the small cells, we parallelize the chunks of cells, all right? And then it's very similar to chunking in the traditional sense, but the data needs to be grouped in a special way. So the material data set needs to be whole within that chunk effectively. Yeah? And this, whether we use a standalone PC or Databricks, was always the case that this vastly improved performance. Here's what the original approach looked like. As Dan said, it was a standalone on my laptop, actually on this laptop, and it was using R and R-based solution. We were extracting historical issue data from SAP HANA, and we were doing this on a site-by-site basis, so extracting data from site number 1, and then we'd input it into R, and then we'd distribute it using the Parallel R package. Now, we started off on the laptop, and then we used a offline, high-performance 48-core PC. And that worked reasonably well. It managed to go through the solution, but in this iterative fashion, it took a total of 48 hours to do all the runs. Okay? So, given that we're going to have more assets, 48 hours, and we may need to run this on a daily basis, so We're not there yet. So the next step was, how do we scale this up? And I think, it was working with Databricks and Spark. This was the obvious solution. So to use the SparkR API framework to do it. And that uses, how we actually implemented it was a function called gapply in the SparkR library. And I'll just give a quick example of what it looks like. It's actually a very simple thing to do. And in terms of the presentation, there's not a hell of a lot to say, but I can just run you through the anatomy of this gapply function, okay? So what we have is a worker function, which looks like so. And this is distributed across these groups of different materials. We have the input data set here called boot in, and we have a column here, a key, which represents the groups. This is not at the individual material level, this is at the chunking level, effectively. Yeah? And here, this is where it actually simulates, this is using our code to basically simulate the material lead times, and down here, a bit further on, is using a by command here to iterate and apply the Bootstrap on each one of the different material historical data sets. The only other aspect of it here is you have to specify the schema, the output schema there. So it's deceptively simple, okay? It's very simple to do, and it's minimal code changes. And with doing that, we greatly improved the performance, yeah? We're still running it in the same way, so the architecture kind of looks the same. It's just that we have a bigger scale-up now. And we actually used a 50-node Spark cluster, and we iterated across the different shell sites, and then we reduced it from a total of 48 hours down to 4 hours, yeah? Because we have that extra computational power. What's also nice about it as well, you don't have to explicitly state how you parallelize the problem. Yeah? Spark implicitly does that for you. Yeah? This is an embarrassingly parallel problem, but it was very simple to scale up. However, that's not the end of the story there, as it were. Okay? And with working with Databricks, they came up with an idea, and we implemented it to pipeline the problem. Okay? So in the way it was previously done, how it was working was iterating through each data set, one after each other, in a kind of for loop. And the reason we did this is because we built it for one, and when we were asked to scale it up, we naively, if you like, just created a for loop around it and rolled it across the asset. This is naive. And if you can restructure the problem to make it independent of asset, in other words, bring all these data sets together, do the pre-processing so you can independently distribute each one of them cells there, then you have a really big performance benefit. Yeah? So it's gone from 4 hours down to 45 minutes. Okay? And that's because it's reducing latency. In this kind of for loop structure, it's distributing the jobs, and then it's across the 50 cores, and then 49 of them might finish, and then you're waiting for that final one to finish before you can move on to the next job, okay? But with this pipelining approach, there's none of that latency. Once it's finished a job, it just can go out and grab another one, and another one, and another one. And that is, a key performance issue here. So I would close out by saying, in terms of my takeaways from this, is that SparkR, really easy to scale up the problem, yeah, and roll it out, okay? But herein is the danger there, right? Is that, the risk here is you don't really think about it. And there's two aspects here that we did that was important. Number one was chunking, yeah, recognizing that if you distributed too many small jobs, the overhead in the distribution of the job reduced your performance, big style, yeah? And secondly is re-architecturing the approach, so you pipeline it so you reduce latency, and that really, really improves benefits. Back to you, Dan.
Great. Thanks, Wayne. So I just want to finish off by bringing it back to the business side of things. And I think what's really important to understand is what we were able to do here was because of the technology that Wayne was talking about and the way we approached the problem, we were able to take a tool which previously would have been fairly localized to a single region and turn that into a global product, which actually is now becoming the foundation for the way that our inventory analysts will do their work. And what's also important is that by making it available as a digital solution, and what I mean by that is a web portal with all the information in it that the inventory analyst needs, we were able to change the way that they do their jobs on a day-to-day basis. And actually, what's interesting is, firstly, because they were embedded into this project from the start, and they dictated the data they wanted to see around the algorithms that Wayne described, they're starting to use the tool that we've developed in ways that we hadn't previously envisaged. So they're using this to do dormant stock reviews, to identify things that aren't moving very quick, in addition to the materials requirements planning, which we talked about. They're also using it to identify the bills of materials that they need for a particular piece of equipment, because they can look at the whole history and start to bring out what are the spare parts which are typically used against any given equipment class. They're doing proactive inventory reviews, where previously it was always reactive to changes in the business. And they're also making changes to the lead time based on the lead time simulation work that Wayne talked about. They're able to much more accurately update the system lead time, which helps with all sorts of other planning activities. And so what's very exciting about that is we see the impact of this, and by bringing together a cross-functional working team that included people from IT, from the data science group, from data engineering, from Databricks, and also project manager, and of course, most importantly, deep business experts who wanted to shape the product, we were able to go far beyond the data science and actually make something that's really powerful and is now working and is becoming a key part of the way that they do business. And so where are we now? We're now partnering with our global IT organization to roll this out initially across Upstream. Upstream is just going live at the moment, and we'll roll this out shortly across the global downstream business as well. Because the way we've approached this, because the scalability Wayne talked about, actually it's pretty easy to go from a single asset to multiple assets to a global deployment. We're also looking at independent use of the algorithm. So the algorithm we built potentially has many other applications, both for ourselves but also for our partners, for businesses that we work with in our downstream and joint ventures in our upstream. And so we're talking to them about, can we help them with having similar problems in their businesses? And finally, and perhaps most importantly, and I'll give a shameless plug for my talk tomorrow, this is all part of a plan to build out a Shell-wide analytics capability, which is core to our digitalization strategy and where we want to go as a company. So I'll leave it at that. We're in time, which is amazing. So I'll just say, are there any questions?
Yeah, great talk. I was just wondering about the ggplot function that you did in the OR function. How much were you able to take the OR function that you had and just literally port it over almost line for line, or was there much work involved in changing the OR function to work in a Spark environment?
There wasn't hardly any work. It just rolled out. Yeah, there's a little bit of nuance there, but that's the danger, right? Is that people just do it without thinking about it. Yeah, but it's easy to scale it up. But for this problem, obviously, because it's an embarrassingly parallel problem, other problems may not be the case.
Yeah. Are there any other questions?
Yeah, maybe if one, maybe less technical. But what I'm curious about is Shell is a huge organization. Did you meet a lot of resistance when rolling this out? Because obviously you're automating a lot of specialist work there. Was that easy, or did you have special tactics for that? Or?
Yeah, great question. It varied dramatically. So what we found was the reaction from different assets was actually very different depending on where they were. So if you looked at the Gulf of Mexico, there they had 3 or 4 very enlightened individuals that had already been looking at the potential of advanced analytics for their business. And they were very, very keen. And so the initial pilots were really smooth. There wasn't an issue. They were part of the team. It was a one-team mentality. When we came to deal with the group MM team, and then also some of the other assets team, there was a lot more resistance because you had a bit of a not invented here syndrome, that they hadn't come up with this. It had come out of a group in the Gulf of Mexico, and then they were effectively this was being superimposed on them. And so where we were able to overcome that was by getting 2 or 3, we put together a network of inventory analysts to help shape the tool. And the challenge was, and this is where the science and the change management came together, we actually had to make some changes to the way that the tool presented information that we didn't purely agree with. We thought actually they were pretty silly. But the point is that to get the buy-in, we had to make some compromises because they needed to feel ownership. They needed to feel that they'd shaped the tool that came out of the project. And that was pretty challenging, to be honest. So it's definitely been a journey. I'd encourage anybody who's working in this space to recognize that it's as much about the people as the technology and the data science. And it's bringing all that together that's really going to drive the benefits.
What I'd say, Dan, is people are more willing to adopt and if you bring them on the journey with you, right? So we've had projects where we've gone away perhaps and built a solution and shown it to the customer and they've rejected it almost but if you bring them on the journey and let them have their input, right, they're far more likely to adopt it, and as a consequence is far more likely to be successful.
One last question. It's actually a similar topic maybe. You mentioned that you produced a lot of the algorithms that were predicting stocks, and one of the comments you've made was that it helped a lot of decision making.
Yeah.
So and I think it's great that you talk so much about how do you build a product around that, because I think that's a missing part in many of these data science projects. So I was wondering maybe in 1 minute if you can tell us a bit more about how you drove this process. So, for example, in some cases you mentioned that the analysts were requesting some specific type of information. So was it impacting the way you design the algorithm, or was it that your algorithm does one certain thing and then you just think about how you can visualize that, etc.? So if you could maybe shed some more light on that, it would be great. Thank you.
Are you talking specifically about this use case, or also how we do it with other use cases?
In general, but maybe this use case is easier, right? Because, for example, you mentioned that to get 90% uptime, it's 10 items in a stock. To get 95 is 30. So how do you deal with this requirement/product cases, essentially?
Yeah, so I'll have a go, and then maybe you can jump in. I think there's a few things. So we adopt Agile. So as a methodology, we start with Agile. So in that sense, we treat it more like you would think about developing a mobile application than potentially a traditional data science project. So it's a bit of a both and. What normally happens is we get a problem statement. So in this case, we're really strict on the definition of the problem statement. So we always say a good problem statement is one step in one process affecting one person. So can you actually identify that core pain point, that user friction that says, I have an issue here? And in this case, what the issue was is the inventory analyst was tasked with updating those 2 reorder points, and they didn't have any way of, there was no support for them in doing that. It was left to each inventory analyst with some sort of procedural guidance to say, how do I do that? So that was the friction, that was the problem statement, and that was what they wanted us to solve for them. What we then tried to do was do 2 things. Wayne did some initial exploratory work to say, can we actually build an algorithm based on the data that will help set those reorder points? And then the second thing that we did was we also developed user stories and a product backlog around what data do they want to see to help them make that decision. So it was not just about the recommendations, which we knew were going to be very, very important because that automated the problem, if you like, but it was also about the surrounding data, which they didn't currently have in one place, that would help them make a better decision. Because what we found is, even if the algorithm was right, they didn't always believe it unless they saw the surrounding data. Does that answer the question?
Let me just enlighten a little bit more on that. So from my perspective, how it works more on the technical detail is, instead of just giving you one optimal stocking level, what it does is it gives you a combination of different stocking levels for different service level requirements, right? So it's 80%, 85, 90, 95, 99, okay? However, backed up, so that's the first stage in the process, and the second stage in the process is then giving a recommendation about what service level you think this material needs to be. And that's we use more data sources to see, was this an unplanned, when was this used? Was it associated with unplanned maintenance? Was it associated with a planned maintenance? And all the kind of other data on top of it, which gives you a little bit of information as to what the criticality of that material is. In fact, that's how we do it effectively, give it a criticality score. I hasten to add it is a suggestion. And, it is up to the analyst effectively to make the choice. Yeah, but it's wrapped up in a way that is easy for them to see all the analytics around this.
Thank you very much, gentlemen. It was a great presentation. And let's give a hand.